So I'm going to talk of temperature control of very small systems and systems on paper, in computer, not real systems. I'll start with why temperature control, why we want to do that, and the moment we talk about temperature control, what is temperature, turns out there are many different types of temperature. So a history of how temperature concept came to be. And then in molecular dynamics, which has become a very powerful tool across all areas of science and technology, how that is done in molecular dynamics, and some of the open problems in the area. So this is the starting point, that let us say we have a beaker full of water in equilibrium, and we insert a thermometer with a bulb in it, and the thermometer comes in thermal equilibrium with the water. The mercury stops at a certain reading, and that reading is the temperature of the liquid. Essentially what is being used here is the zeroth laws of thermodynamics, which also happens to be the last one to be stated formally. Now interestingly, if I now put a temperature gradient, a heat flow in the system, heating it at the bottom and keeping it ice cold at top, then this is the situation. What temperature is the thermometer measuring? Does it depend on the material of the thermometer? Does it depend on where the thermometer is placed? Does it depend on what sort of interaction the thermometer has with the liquid? Is the thermometer coated with a reflective substance or not? Many questions are there. So in essence, the question is that the zeroth law of thermodynamics is not valid here. What is the temperature and what is the thermometer measuring? So in equilibrium, all these temperatures are the same. This is a very new concept of temperature in the late 90s. Kinetic temperature more than 100 years old. Configurational also 80s and 90s. Then thermodynamic mid 1800s. Statistical late 1800s. Entropic around that time. Which of these is measured by the thermometer? And if you want to simulate in the computer this process of heat flux in that beaker, which ones shall we measure? Which one shall we try to control on both ends so that the heat flux is there? And this is a very interesting and open problem, really. Another thing which shows up in the area of dynamic fracture, for example, that this slab is being pulled in mode 1, and then as the crack is propagating, these are the snapshots of temperature. As you can see, on the left we have kinetic temperature. I'll define what that is. On the right I have configurational temperature. I'll also define what that is, and they're very different. And no one can say really which temperature is the one that matters here. And if you are measuring it during simulation, or if you want to control some of the temperatures maybe on the borders of the simulation box, which one should we go for? So to summarize, why do we need temperature control? Because not everything happens in isolation. Not everything is an NVE, the microcanonical ensemble. These real experiments happen by exchanging energy with the atmosphere, the environment, some reservoir. So we should be able to do temperature control which would be consistent with the physics of the problem. The interaction of the reservoir must be proper. The microscopic reversibility, which is one of the hallmarks of dynamical equations, must or should preferably be retained. And then while doing that, we'll also talk about the shortcomings in present or devolving temperature control methods. And all processes in real life are to some extent non-equilibrium in nature, irreversible in nature, so the states are not in equilibrium. So we want to find statistics of these non-equilibrium states. Now, the history of temperature. I already talked about the 0th law, which is the latest entrant in the canon. It basically allows us to create sets of isotherms, that if I say that the temperature of this liquid is 30 degrees centigrade, it means that the temperature with which the thermometer which with measuring the temperature was put in a known system of 30 degrees, and hence if this measuring the same thing, the other thing must be also at the same temperature. So, this transitivity of temperature is assured by the 0th law. It, however, does not talk anything about heat flow or heat flux. Then this is basically a logical sequence. This is not chronological sequence. Then gas laws, which took almost 200 years to perfect. And then this gave us, the gas laws gave us the equations of state and a hint of absolute zero. If you draw pressure versus temperature constant volume, you will see that there is a graph kind of points towards minus 273 Celsius. So, that was the first hint of absolute zero. During the first half of the 18th century, the scales which we still use today started being developed. And by the way, does anyone know why Fahrenheit scale is 32 at melting ice and 212 at boiling? It's a very interesting thing. Fahrenheit was not a crazy person, really. Well, he was crazy in some other reasons. His zero, he actually had a zero. That was the equilibrium of brine with ice, salt water with ice. So, he set his zero at brine and ice equilibrium. And his 100, he didn't have 212, he had 100. His 100 was the temperature of a healthy adult, which turned out to be his wife. So, that's how 0 to 100 was developed, and then later that was extrapolated to melting ice and boiling water. Celsius, of course, did that directly. Then the Carnot's theorem, which was the first hint of material independence in something like temperature. Basically, what in these times, heat was still thought to be a fluid. It was not known to be energy. So, Q2 by Q1 was material independent. So, that was the first hint that Lord Kelvin used almost 25 years later to say that, okay, so that Q2 by Q1 must be a ratio, must be a function of temperature, absolute temperature, and he proposed that be a ratio of the hotter and the colder reservoir. So, things started moving very fast after that. The first law proposed, that was the first time that heat was equated with energy, and that was the first conservation law in thermodynamics. Then the non-conservation law, something that keeps increasing, and this is the first time that there was a direction of heat flow, and some processes may happen, some processes may never happen. And this is the first time it was clear why, or at least under what laws heat may never flow from colder to hotter body. Then the kinetic theory of gas, which first time used the particulate nature of matter, and was very successful in basically defining temperature as the average kinetic energy of a substance at equilibrium using equipartition theorem. So, that gave us, during that part of the 19th century, the Maxwell-Boltzmann distribution, equipartition theorem, and temperature as the variance of the velocity. And the third law, which was early part of 20th century, says that absolute zero is not attainable in finite number of steps. And then, so this is how the entire theory of heat and thermodynamics and temperature equilibrium and non-equilibrium started growing, and it hasn't stopped today. The very thing that we talk about temperature today still took time to evolve. So, as late as the 1990s, the thing was still being refined as how laboratories can actually come up with their own temperature metrics and standards. So, there are several types of temperature. When we combine the first and second laws of thermodynamics in equilibrium, this is all very well known, that we have ds as the internal energy plus the reversible work done on the system divided by the absolute temperature. And that gives us two expressions of temperature. One is involving the state variables and the other involving the fluxes. And this has been so successful, it has been also extended to black hole radiation. But in non-equilibrium, some of these classical concepts like entropy, they are not really defined. Efforts have been made to define them away from equilibrium under what is known as so-called local thermal equilibrium assumption. But this definition more or less strictly does not apply. Then there is the kinetic expression of temperature. What this says is that the average kinetic energy of a set of particles in equilibrium, and if they are the same in all direction under that assumption of equipartition, equals each of those contributes half kb times t, and together the half mv square ensemble average would give me 3 kb by 2. So that is one of the most celebrated relationships in statistical mechanics. But again, when you have heat flow in a certain direction, when you're making sure that there is energy transport only in one direction or the others, in such situations, this equipartition is no longer valid. And also, if there are temperature gradients or other non-stationary things, then this equality is no longer true. This gives us that temperature is related to the variance of the particle velocities. If we move to Maxwell-Boltzmann distribution, then temperature becomes the variance of the velocity distribution. So here we have, this is the so-called canonical distribution, and this holds a fundamental place in temperature control because when a system is in contact with a heat reservoir, this is the limiting distribution that we want for it. So this is of course Gaussian in nature, at least for the velocities. This is the kinetic energy part, and this is the potential energy part. Now, these distribution functions don't exist away from equilibrium, and work is still going on to find a unified framework. In the 90s, this paper was published in 1998. This was a major breakthrough in generalizing temperature away from the kinetic angle. And that happened, let us start with, that happened basically looking at the curvature of the constant energy surface. So what Rugh did was, well, let's start with just a 2D problem, an undamped harmonic oscillator, and its equation of motion is given by x dot is partial of Hamiltonian with respect to p, which is in this case p by m, and p dot, the momentum, degree of freedom, that changes according to the force minus partial of Hamiltonian with respect to q or x, and subject to some initial condition. Now, if you plot this in the phase space in px, then it becomes an ellipse, as is very well known. If we generalize this to 6 n dimensions, where there are n particles each with 3 displacements and 3 momentum degrees of freedom, then this is the Hamiltonian. Hamiltonian for isolated systems is the total energy, but when we talk about Hamiltonian mechanics or Hamiltonian dynamics, it's basically that function whose partial derivatives gives the rate of change of the coordinate systems, the x and its conjugate p. So when we generalize this particular phase place, this ellipse in px plot in the 6 n dimension now becomes a surface. Now, Rugh very intelligently realized that the curvature of this constant energy surface can be related to a temperature measure. And so this is the ensemble average. Whenever we have brackets like that, they are the ensemble average. And as you can see, this is the curvature of the energy surface. And then under the ergodic hypothesis, which I'll come to in a minute, that just is a long time average of the same quantity. In the next few years, this was generalized to other distributions, the other ensembles. This particular one is valid for the so-called microcanonical, as I said, which is NVE, a system isolated from the universe, fixed number of particles, fixed volume, and fixed energy, which again is not very useful to us because we want to look at systems which interact with the surroundings. And that's the whole reason we want temperature control. So this has later been generalized to canonical ensembles and other ensembles. And canonical basically means our constant temperature ensembles. And then other phase functions. And this is very important. If H is replaced by K, just the kinetic energy, then what we get here is no longer Rugh's temperature, but kinetic temperature, what we always have known to be the statistical mechanical definition of temperature. If H is replaced by the potential energy, here, the potential energy part of the Hamiltonian, then what we get is another very new definition of temperature called the configurational temperature. So that temperature has nothing to do with the molecular motion, the atomic motion, but has everything to do with the position of the atoms. And that is very useful when you have, when you're studying the temperature of a fluid which is moving. It's very difficult to find the kinetic temperature, but very easy to find the configuration temperature. And we will talk about Rugh's temperature, we'll talk about configurational temperature, and we'll talk about kinetic temperature in the rest of this talk. Yes, that's the most important. Sorry, I should have said that. At equilibrium, all the different definitions of temperature are and should be equal, exactly. And we, in fact, towards the end of this talk, I will talk about, I'll show how different temperatures deviate from each other when there is, for example, a steady state heat flux. Sorry? What happens when there is no Hamiltonian? You can still have the equations of the dynamics of the motion. You just do not have the function h, which basically keeps your phase space compressibility factor as 0. So if you have a Hamiltonian, you will have a Hamiltonian if you have an isolated system, which is the constant of the system. But when, for example, many of these equations of motion that control temperature do not come from or are not known to have a Hamiltonian. Some equations, for example, the Hoover thermostat, because of Nose's brilliant work, is known to have a Hamiltonian from which the equations of motion come. And when we say Hamiltonian, we basically just mean this, that you have a function h whose partials would give you the rate of change of the generalized coordinates. A damped harmonic oscillator is not isolated. Well, if it's not exchanging energy, if its energy is constant, then it is still constant energy and you will have a Hamiltonian, if I understand your question correctly. Okay, when we come to Hoover's equation, maybe it will become a little clear. Yeah. Okay, so I won't talk much about the away from equilibrium situations, except that when local thermal equilibrium LTE holds, then some of these concepts, especially the intensive quantities, fluxes, they can still be used in similar formulations as in equilibrium thermodynamics. And this is some of the checks that we can use for basically all these checks is that the higher moments still correspond to a Gaussian distribution for the velocity. So, this is a very limited check of the existence or the validity of LTE when you are trying to use equilibrium statistical mechanical concepts in a non-equilibrium situation. Okay. So, in molecular dynamics, this is basically the schematic that we do. The system is initialized depending on the definition of the problem. If it's a crystal, the locations are given at the crystal sites. If it's a gas, then uniformly. And then the velocities are typically sampled from a Maxwell-Boltzmann distribution at the given kinetic temperature. And then this loop starts. This is the molecular dynamics loop through various integration schemes, Verlet schemes, leapfrog scheme, gear predictor corrector. There are about 3 or 4 of them very popular, about 10 of more if you count all of them. And then, depending on what we are interested in, after this loop, we either reach equilibrium and extract equilibrium information, or if, for example, it's dynamic fracture, we just stop the program wherever we need to and extract the information at the end of the simulation. And this has been very successful. One thing to note here is we run molecular dynamic simulation typically once for a system, and we extract a lot of information from that. The assumption here, and it should be checked, is that the so-called ergodicity hypothesis should be valid. Otherwise, ensemble information, ensemble averages extracted from a single dynamical trajectory really makes no sense unless the dynamics is ergodic. What does it mean? Here, let's just, before I go to ergodicity, this is just a basic MD simulation, as basic as you can have. This is a box of particles originally at a BCC lattice, and there is no temperature control. This is an NVE system, so it's not exchanging energy, and we are just looking at the total kinetic energy, the total potential energy, and the total energy. Since this is an NVE system, you can see that the total energy is constant, but the kinetic energy kind of stabilized at a certain value, and the potential energy also stabilized at a certain value when the lattice adjusted itself. We won't have time to go into this, but this is very interesting. It started as more or less a square shaped lattice, if you remember, but then as the simulation progressed, it becomes like this. The corners kind of bulge out, and this is to minimize the surface energy, which is very high in those corners. So, the atoms are trying to turn into a sphere and minimize that. So, this is ergodicity. Whether we are measuring temperature or density or anything else, it's basically we are taking a space and time average of that quantity. So, in molecular dynamics or in statistical mechanics, the question is that this is the average over many replica of the systems. That's what we mean by an ensemble. We look at nominally identical systems initialized at different microscopic conditions, and that gives us an ensemble. And if we measure whatever phase function that we have in mind, average them over those many ensembles, replicas of the system, then that's what we have as a ensemble average. But that's impossible to measure. We only have one realization of our reality. So, what we do is we instead simulate or observe over a certain period of time and take the time average. And if these two are the same, then the ergodic hypothesis is satisfied. Now, it's a very nebulous concept, this ergodicity. Something may be ergodic in mean but not in variance. It can be ergodic in temperature but not in density. So many things are there. When we talk about ergodicity of a thermostatic system, a canonical system, then it should not exhibit any holes in the phase space, and this is very important because anything that exhibits holes partitions the phase space into two non-communicating subsets. So something like this, if these are the phase plots, phase space plots, is not going to work for an ensemble that is canonical in nature, which means that if you start an initial point, if you take an initial point somewhere here, if you look at the phase plots, you will find that that initial point will only fill up this hole, and trajectories will never cross over from this region to this region, which is not allowed when you need space filling ergodicity. This is a more well behaved, unless there are very minute holes in the phase space, it seems to be an ergodic situation. We actually have found evidence of non-ergodicity in one of the very popular thermostats, which I hope I'll have time to come to. So for controlling temperature in molecular dynamics, there are several techniques available. We group them into basically two main categories. One is deterministic, which may or may not preserve the microscopic reversibility of the dynamics. For example, this one does not. And all the stochastic schemes, of course, do not, because they are basically hybrids or pure Monte Carlo moves. This is the oldest stochastic thermostat, the Andersen scheme, and then the Langevin and stochastic configuration thermostat, and so on. I'll just go through a few of these, the important ones. This PB scheme, P stands for my student Patra and B for myself. I'm not being vain, it is just that Hoover and some of the authors have started using this name for this thermostat, which we proposed some time back. So we are also using the same name here. So the oldest from the 1970s, and this is interesting, molecular dynamics came about in the 1950s. And for more than 20-25 years, there was no even necessity to control temperature. So the oldest one is velocity rescaling. So what is done is that at the end of each iteration, the velocities are just rescaled to match with the kinetic energy of the desired kinetic energy, which comes from the temperature of the whole system. So naturally, there is no fluctuation in the temperature, but the problem is that no dynamical equation can give rise to those instantaneous fictitious moves. There is no force which can do that. So it does not preserve the physics, and there is no known Hamiltonian basis. It does not allow fluctuation. So, and over the years, with the advent of more rational and sophisticated thermostats, this has fallen out of favor. The Andersen thermostat, it's also another physics non-preserving thermostat, but it's easy to understand and it's intuitive. What happens is that Andersen thermostat mimics collision with heavy particles of the heat reservoir, the heat bath in which your system is sitting. You can also switch. You can put switch functions on each atom or particle to say that internal molecules or atoms do not interact with the heat bath, only boundary atoms do. So what you do is that set up the initial conditions, perform Hamiltonian dynamics for all the particles, and then freeze it, make Monte Carlo moves according to a Poisson collision. So you have a rate of collision which is nu, and then nu times delta t, that is the probability of collision, exponential of that in that time period delta t. So you generate a uniform random deviate for each particle. So if that is within that, then you completely change the velocity of that particle, generating it from a Maxwell-Boltzmann distribution. Otherwise, let it be. So if you do it over time, it kind of, depending on what the value of nu is, you have a choice there. You more or less have the temperature fluctuating about a desired quantity. So it's good, it's more realistic in the sense temperature is allowed to fluctuate, and some intuitive physics is preserved, but it's not dynamical in the sense that there is no dynamical equation which gives you these Monte Carlo moves. The equation which preserves dynamics, not in the ordinary sense, but in the stochastic dynamic sense, is the Langevin thermostat. And it has actually been upgraded with addition of the potential energy term also, the conservative force. So this is interesting. Here, if we do not consider this, then naturally you know that the excitations will die down exponentially. But we don't want to do that. We want motion to continue and at a particular temperature. So here, we tweak the intensity of this white noise. These xi's are the white noise, delta correlated noise, such that this alpha, the intensity, is exactly equal to a function, the product of temperature and the viscous drag coefficient, so that the drag is trying to kill the velocity and these random collisions are trying to revive it. So they just balance each other and maintain temperature around the desired value of T. Of course, if you do not have gamma at all, if there is no drag, then this will just blow it up, because this would give you the Wiener process. And if Z is absent, if Xi is absent, then you just have exponential decay. So at equilibrium, again, this equation comes from kinetic temperature equipartition theorem. This equation is not really, as I said, truly dynamical. This is stochastic differential equation, and its interpretation can vary. If you take Ito, it's something else. If you take Stratonovich, it's something else, and so on. The essential problem is that these sample functions of Xi, this white noise, they are continuous but nowhere differentiable. So you do not have the standard definition of integration there. Okay, then this is early 80s, one of the first serious attempts of developing a thermostat which preserves dynamics and it's microscopically reversible. What we mean by that, if there is no frictional loss, then if you just freeze the position of your system and reverse the velocities, you should come back at the initial point. So that's reversibility. And this one does that, and thermostats like these do. So this is same as before for the coordinates. For the momenta, this is the conservative force, and we now add a frictional force here, except that it is not constant. It varies at every step, and one of the simplest way of developing that, the value of that, was just setting that the T dot will be 0. So the temperature will not change. Where from equipartition theorem, that's my value of the total kinetic energy, 3 nkBT by 2. If you just differentiate T, you get a value of Xi as this force F, sum of force multiplied by all the momenta, and then the average kinetic energy. Well, mass is there, not there. So this Xi varies at every step, so it changes with the idea of keeping the temperature at a constant value. Later, it was derived from a much more elegant formulation, which is Gauss's principle of least constraint, and that's how the name of Gaussian Iso-Kinetic Thermostat was given to this. So this was developed independently by Evans in Australia and Hoover in Lawrence Livermore in the early 80s. But again, this has a problem that because this Xi ensures that T dot is 0, there is no fluctuation in temperature, and that is unrealistic. Then this is one of the great leaps of molecular dynamics. Noze, who was in Canada at that time, I believe, he proposed a brilliant solution of the Hamiltonian of the combined reservoir and physical system set, and the 6 n degrees of freedom were there, and he just introduced 2 more variables to represent the reservoir. So the reservoir is of course infinitely large, as we know, with infinite heat capacity, but he just used 2 degrees of freedom. One, and I don't have it here, but I'll talk about it, was S, which later he found out has to be a time scaling parameter, and the conjugate to S was PS, which is in some sense the velocity equivalent, the kinetic energy equivalent of the reservoir. Now, and this we have used in finding the canonical distribution also from classical statistical mechanics and classical thermodynamics, is that the universe, which is a reservoir and the physical system together, is a microcanonical system. It is NVE, it is not exchanging energy with anything, it's isolated. So its energy surface, it's a constant energy surface, and the distribution function of the combined system has to be uniform on the accessible phase space, which is the constant energy surface. So from that point, Nose basically proposed a Hamiltonian form of the combined system, which includes a term involving log S. This S is a time scaling parameter. So now we have a Hamiltonian basis of a thermostat, and when you extract just P and Q for the thermostated system, they follow the canonical distribution. The only problem is that time is no longer real time. That S, which rescales time, it changes from every iteration to every iteration. So that was very difficult to implement and cumbersome to understand. A year later, Hoover did the calculus and realized that essentially what's happening, the conjugate moment of the reservoir can be discarded because it's not so important in the formulation. Just that time scaling factor gives rise to one frictional coefficient of on the system resulting from the reservoir. Again, that friction can be positive and negative. And now that friction coefficient, which is different from what we had before in the Gaussian Iso-Kinetic, if you look at this, Gaussian Iso-Kinetic gives us just xi in terms of the coordinates. Here we have this frictional coefficient eta is an evolving quantity, and it is either positive or negative depending on whether the kinetic energy is greater or smaller than the desired temperature of the system. So this was a great intellectual leap. It's the first time that we had an equation of motion that was reversible and that maintained temperature around an average value. And at that time, this was, Ishan, to answer your question, this was not derived from a Hamiltonian. This does not have a Hamiltonian basis. There is no H which would give rise to x dot as this, p dot as this, and eta dot as this. But well, that would be a completely different approach. If you remember that Rhu's approach to temperature was from the curvature of the fixed energy surface, that did not have any such frictional term. So even when that was extrapolated to a canonical system, there was no term involving a frictional coefficient and its evolution. So these are completely different things. And when you control a temperature using Nose's equation or Nose-Hoover equation, you're essentially controlling the kinetic temperature, because this comes from, again, equipartition theorem. This T is nothing but kinetic temperature. The question is that if I use this scheme of controlling temperature in a non-equilibrium situation, what sort of temperature am I getting for the configurational part and the Rhu's part when I'm just controlling kinetic temperature? And we'll come to that. I already talked about these, so I'll skip to the next slide. So as I said, why so popular is first truly reversible deterministic thermostat which allows fluctuations. It is not ergodic for small systems. So what we mean is that when we do it for a one particle 2 degree of freedom system, there are the dynamics that we get by controlling its temperature with the Nose-Hoover scheme. It's not space feeling, so which means that it does not correspond to an ergodic dynamics. So that gave rise, just about 10 years later, this Nose-Hoover chain thermostat, or this MKT thermostat, which used a chain of coupled thermostats. So if you remember, this was the original equation, and then I have eta, as before, there is a mass here now to the thermostat, and then eta is not only related to the temperature of the system, the desired temperature of the system, but another reservoir with xi, and then that evolves according to interaction with eta. So it's a chain thermostat, and you can create chains as long as you like. Typically people stop at 2. And then it was thought for several years that as long as you have 2 parameter thermostat or more, the dynamics you get for your physical system is ergodic, but that we just hoped we are proving that it is not true. There are still some holes of non-zero measure left in the phase space when you simulate with such dynamics. So currently I believe that this Nose-Hoover chain is the most popular and trusted way of controlling temperature. Some months back, my student and I started wondering at temperature and how we can control Rugh's temperature, and it stuck to us that instead of a chain thermostat, we should have 2 independent thermostats, one to control the kinetics and another to control the configurational part. So we have this xi for the configurational part and eta for the kinetic part, and together using limiting long-term fluctuations and equating the distribution to the canonical form, we came up with 2 equations of evolution of these 2 independent thermostats, and this actually does much better than the Nose-Hoover or the other configurational temperature controlling thermostat there is, Travis and Braga's thermostat, in non-equilibrium situations, and I'll end my talk with that. So this is one of the very important benchmark problems that one should solve when one should compute when comparing thermostats or finding the efficacy of different thermostatic schemes. So steady state thermal conduction, we have 2 reservoirs, one at high temperature, and this is a periodic system. So on the left we have a cold temperature, a cold reservoir, and on the right also, and the system is basically between these 2 that we are studying. So it's a very small system, 2000 particles, and we just divide the system into 10 bins and see how the temperature is varying when all we are doing is basically controlling the temperature of the system that is in touch with this reservoir and that is in touch with this reservoir. We are not controlling the dynamics of something of the atoms that are in between. So when we use Nose-Hoover thermostat to control the strips, we observe something interesting. That Nose-Hoover is in this non-equilibrium conduction problem, it's not able to control the configurational temperature at all. This is 3 is the hot temperature, 1 is the cold temperature. So the top pink line is the kinetic temperature, which is at 3 because Nose-Hoover is a kinetic thermostat. But the top blue line is the configurational temperature, which, remember, it comes from just the coordinates of the system, not with the velocities. And it's not doing well at all in this. But for the colder, it does reasonably well for both. When we use our thermostat, since we are controlling both, all degrees of freedom, we are able to control both the kinetic and the configurational very well at both ends, and in the middle also, which is between the thermostat and ends, and that is here. So this end, this in middle region, and we are not thermostating that at all. So it will take 1 minute, then I'll be done. This blue is our thermostat, so this blue group is our thermostat. The red group is Hoover's thermostat, and the green group is the configurational Bragg-Travis thermostat. And the solid lines is the kinetic temperature, and these vertically hashed lines is the configurational temperature, and the vertical, this horizontal hash lines is Rugh's temperature. So as you see, as we talked about, Nosy-Hoover thermostat controls kinetic perfectly, but is not able to control the other two, and not only at the ends, but also intermediate points. The configurational thermostat does better in the intermediate regions, but not so good at the ends. But our thermostat, which is the blue set, does remarkably well in controlling at the intermediate points as well as the end points. So that made us very happy. And the proof that local thermal equilibrium is satisfied at each of these strips, we just made sure that the temperature coming from the second or the fourth or the sixth moment of the Gaussian distribution are still all equivalent. So I end my talk with some of the open problems. There is no known Hamiltonian basis for, I just said something wrong. There has been a paper which just came out with the Hamiltonian basis of Nosy-Hoover's thermostat. But the Hoover-Hollian thermostat, which controls higher moments, or the configurational thermostat, or the one that we proposed, we still need to derive the Hamiltonian form for those. Now, which temperature is more important? Which one should we control, or which one is actually temperature in non-equilibrium situation? And Hoover strongly believes that it's kinetic temperature. Kinetic temperature is the only temperature worth the name, nothing else is temperature. And then this is also an open question that if I am generating a canonical distribution, then it must be space-filling ergodic. But these thermostats don't do that, neither does ours. So how do we impose ergodicity on the resultant dynamics? So these are some of the open questions, and I should acknowledge 3 students especially over the years. Chang Lu, who helped me with the original molecular dynamics formulations, Ujjal, who started with me on this different definitions of temperature, and Puneet, particularly this Puneet PBP, this is mainly his development. So thank you very much. I'm open for questions.
So your PB thermostat, it's a good name. It's is it motivated by the Rugh's temperature concept?
Yes, exactly.
So I can see that there's a curvature term coming in.
Yeah.
Okay, that was one thing. And the other thing is, so if you are doing this non-equilibrium system, like you have like a constant, so I'm curious about why Nosy-Hoover does not control the hot temperature, but it does well in the cold temperature. So why is there a difference? How does it know which is hot, which is cold? You had those red lines, and the one before this.
It's the same thing what we showed with the movie, that this is grossly off, but here it is not. I can only conjecture. I don't have an answer, but at higher temperature, a lot more of the energy is contained by the kinetic degrees of freedom. Maybe that's, and at lower temperature.
So, but it's worth checking. I think it's a nice conjecture, but it's probably worth checking the difference as it grows with how it changes with temperature.
Yeah.
Thank you.
So in the PB and the one other thermostat that you mentioned, there's a momentum sink. There's a momentum is being lost to somewhere. So
Okay.
is that the reservoir that's taking up that momentum?
Yeah, let's do with nose Hoovers, because that is simpler and the original one. Yeah, so this is the only contribution coming in the equation of motion from the reservoir. But this is not a frictional coefficient in the usual sense, because it evolves. It sometimes is positive, sometimes is negative. Its evolution equation is given by this, which comes from trying to match the resultant dynamics with the canonical distribution. So depending on whether you're above or below the target, it will become negative or positive.
Sure. But you need the reservoir to absorb or give momentum as per your requirement.
Yes.
Right? So in other words, is that physical always? I mean, I can understand a thermal reservoir, but when do you have a thermal reservoir also being a momentum reservoir? Is my question.
That's a very interesting question, but just by extending the logic of a thermal reservoir, if you again take the partial view that the thermal part of any energy is basically kinetic energy, then it's the same thing, right? It's basically, it is a kinetic reservoir which is either going up or down. It has infinite ability to do this adjustment. There is a fourth equation which is for its conjugate, but it does not come in the picture at all, so which is why.